So to wrap up our discussion on system on chip design, we are going to look at some high level design challenges that come up in the context of system on chips. At a very abstract level, right, these can be sort of summarized over here. Power consumption, how do you handle the power requirements of large SoCs? How do you verify and how do you debug these large SoCs, and what are the sort of implications for security when you are trying to implement such things? Now of course there could be other challenges as well, so at this point all that I am doing is looking at these from a high level point of view in order to sort of just pinpoint a few specific issues that need to be kept in mind, but this is not an exhaustive coverage of everything, that all the kinds of challenges that come up. So let us look at the notion of power consumption in digital systems, right. We have already looked at this briefly in some in some context, which is, we know that or rather we have seen that the dynamic power consumption of a circuit is related to the so called switching activity. In other words, when there is a transition of a signal from 0 to 1 and then from 1 to 0, there is some charging and discharging of capacitances that happens. That capacitance is basically the sum of the individual capacitances across the different gates in the circuit, and the larger the circuit, the more the capacitance. Now it is also related to the supply voltage, and interestingly it is actually proportional to V squared, right, because our energy per transition goes as CV squared. It is also related to the number of times you are switching per second, which is basically the operating frequency, or more accurately the switching frequency of a particular node in the circuit. Now in addition to this, which is the dynamic power, which is the dominant part of most modern digital circuits, you also have static power, which is basically a leakage current, right. Ideal CMOS circuits do not have leakage because at any point in time either the PMOS or the NMOS transistor are off, but well, that is theory. In practice the transistors are now so small that yes, there is some kind of leakage that still happens and cannot be avoided beyond a point. There is also something called short circuit power, which is literally a small amount of energy that gets dissipated during the transition while one transistor is switching off and the other one is switching on, and in between both are sort of simultaneously on for a short amount of time. So there are various components of power consumption in any digital circuit, right. Now modern SoCs, given the fact that they are dealing with literally hundreds of billions of transistors in the worst case, have to deal with a number of additional problems, right. Process node scaling has led to increased leakage, right. There are a number of things being done to sort of mitigate the effects of leakage, but it still exists. The sheer number of transistors means that even a small amount of leakage or small amount of energy being dissipated in each transistor sort of gets multiplied by the number of transistors. The frequencies at which we are operating have been going up. Of course, they've kind of stabilized for a while in the sense that once they went above maybe 1 or 2 gigahertz, the growth in frequencies has sort of stopped, but those are still extremely high frequencies and basically contribute to very high power dissipation. What all this means is that when you are trying to integrate all this onto a limited amount of silicon die area, the heat being dissipated tends to or rather the power being dissipated over here translates into heat, and being able to dissipate that heat without actually damaging the circuit that you have is itself a very challenging task, right. And this becomes even more of a problem with battery powered applications where the heat is one part of it, but the energy consumption, in other words the battery life, also plays an important role, right. So you have many different things that you are trying to balance, right, performance versus power, the battery life, thermal management, and all of these also have implications for reliability, because if you heat up a circuit, its lifetime tends to degrade. In other words, how long you can use it at a high temperature is typically lower than how well you can use it at lower temperatures. So what are the techniques that we can use for actually reducing the power consumption? We are going to look at a couple of different options over here, but this is not by any means exhaustive, right. Clock gating essentially says that we can selectively disable clock signals to unused parts of a circuit, right. we can do a number of things. There are so-called latch-based clock gating techniques, or you can have an AND gate before the clock signal actually feeds into the flip-flop, and by giving a 0 control signal to the AND gate, you turn off the clock transitions. So the flip-flop by itself does not see a transition, and therefore the flip-flop remains sort of in frozen mode, and there are no transitions at the output of the flip-flop, right. So various kinds of hierarchical clock gating techniques, where you can basically turn off the clock to an entire subsystem, or having clock gating cells that are integrated within parts of a design. All of these are circuit level techniques that are commonly adopted in practice. Now all of these in turn have impacts on various aspects of the design process. Clock tree synthesis is something which we have not really touched upon much, because it has more relevance when you go down to the transistor level and start designing at the level of integrated circuits. But a clock tree happens to be a very important part of how the clock signal gets distributed across the entire circuit, right. In FPGAs, which is the primary target we have as far as this course is concerned, clock trees are already sort of taken care of by the FPGA fabric itself, so we don't need to worry too much about them. But in ASIC design, this can be a fairly significant additional complexity. There are a number of different timing implications when you are trying to sort of do clock gating on the clock tree synthesis. There are a number of tools that help with automating parts of this, right, and without that, essentially this kind of clock gating techniques would not be possible in practice. What about power domains, right? Power domains are, as I mentioned earlier, you could have multiple supply voltages in a single design, and it's common to have 6 to 10 supplies in a single design. You might have 3.3 volts being used for communication to maybe external RAM devices or to IO peripherals. Similarly, 2.5 may be for communication with memory banks. 1.2 and 1.05 are common voltages for the core voltage, in other words the operational voltage. You could go below that, 0.8. There could even be certain kinds of blocks that operate closer to 0.5 volts, right. Now those kind of blocks are now operating close to the threshold voltages of the transistors, which leads to other problems of its own. The good part is, by having lower voltage, they consume lower power, but on the other hand, there are other implications for operating at low voltages like that. Now the good thing of having multiple voltages, or having in general controllable voltages, is that you can also add transistor switches, right, into your supply path, which means that it's possible to turn on or off a complete segment of a circuit, right. You could, for example, have a transistor literally in the supply rail leading into a module, and by disabling it, the entire module is shut off, it does not get power at all, and therefore it does not also contribute to power consumption. Now what that means is, at some point in time you will probably have to turn it on again, which means that you have to deal with these power state transitions, a large rush of current that typically happens as and when you turn on individual blocks, right. How do you design your power grid or your power supply lines in such a way that it can actually deliver the amount of current that is required? How do you sort of separate out the cells that cross the boundaries between different power domains? Because let's say I have one transistor giving a 3.3 volt output, trying to feed into another one that has a 0.8 volt maximum VDD, right. What it looks like is, even this 0.8 over here is going to be seen as a logic 0 by the 3.3, and in turn the 3.3 might very well end up damaging something which is working with a 0.8 volt supply. So you need some kind of level shifters for all of these voltage interfaces, so that they continue working as digital voltages. Now once you have this notion of different clock domains and different power domains, it is also possible to do dynamic voltage and frequency scaling, which means that at runtime we actually change the voltage as well as the frequency based on the workload. Now given the equation that we had, right, which is basically saying that we have C V squared F, right, it turns out that F is also proportional to V. In other words, the higher the voltage, the lower the corresponding operating delays, and therefore the higher the operating frequency. What that means is that if we just do voltage reduction alone without worrying about the frequency, it is possible to get, or rather by also scaling the frequency, it might be possible to say that we could get a cubic power saving in voltage reduction. Because let's say that I want to operate at a lower frequency, I can also then operate at a correspondingly lower voltage, and the net benefit is going to be a square factor, a quadratic factor from V square, and also a term from F, finally giving us a proportional to V cubed reduction in the power, right. Whereas on the other hand, let's say that I decide to just keep V fixed, I do not change this, but I just reduce the operating frequency, I can get linear power savings just by reducing the frequency itself. Obviously there is a cost to this, which is that now the time taken for the computation increases because the frequency has reduced. I need a greater amount of time to finish whatever computation I was trying to do, assuming that it needs the same number of clock cycles, right. Now that is fine, that is essentially one knob that allows us to say I can reduce the power if I need to. The flip side of course is that it is going to take longer to perform the computation. You can also think in terms of what happens as a result to the total energy. Let's say I bring down the frequency, right, I get some kind of saving in power, but then it takes longer to finish the computation, so the total energy consumed might still end up being the same. So then why would you do something like that? Well, by bringing down the power, you have brought down the heat being dissipated, and therefore the cooling requirements of your system might reduce, right. So there is still some benefit even if you just reduce the frequency, even if you do not maybe get a total increase or improvement in the energy consumed. So in order to do this kind of thing, of course, you need an lot of extra logic, right, and circuitry. You need voltage regulators, clock generators that can generate different frequencies, various kinds of performance monitors, and also the control algorithms, which are either finite state machines or software controlled algorithms that allow us to switch between the different states. Now, the voltage regulators and clock generation are actually typically mixed signal components because they are the interface between the analog world and the actual digital world that is being controlled in this way. Now just as an example of the kind of savings that you can expect, assume that you have, let's say, some processor that is running at 1.8 volts and a 2 gigahertz frequency. This is what I would call as 100% performance, right, and the performance ultimately is just determined by the clock period or clock frequency. So I am saying that something running at 2 gigahertz is basically giving me 100% performance. It's also, this is the maximum power that is going to be consumed. On the other hand, let's say that I manage to drop the frequency to 1.2 gigahertz. Just based on the clock frequency, I have basically a 60% performance of peak, right. This is 60% of the peak performance. What about the power consumption though? I managed to bring the voltage down from 1.8 to 1.2 and the frequency down to 1.2 over here, right. So I could sort of say that my savings in power, right, is the capacitance remains the same in both cases. What I have in the new case is 1.2 divided by 1.8, right, squared, and the frequency basically comes out to be 1.2 gigahertz divided by 2.2 gigahertz, right, which basically works out to be in this case 4 by 9 into 0.6, right, which is approximately around 26% or so, right. Now the fact of the matter is you may not get an exact 26% reduction in power consumption because there might be other aspects that come into play when you actually change the voltage, but you can expect to see somewhere close to around 26%. I can't even say, this 35 is not like a hard cutoff or something, but I can't really expect to see more than 26% savings, or rather not 26% savings, a reduction to 26% of the original, right. Similarly, I could go further. So what I would have in the low power mode would be a ratio of 0.9 divided by 1.8. This is the V squared component, and I have the F component, which would basically give me something like this, which would work out to somewhere around 7.5 to 8% of the original power. So I can get like 1/10 of my original power if I am willing to sort of go down to a low frequency as well as a low voltage. Now some of you, especially if you have a Linux laptop, it might be worth running. So there are certain tools like PowerTop and PowerStat, which actually can give you the dynamic power being consumed by the system that you have, right. So on Windows also you can have these graphical monitors that show you the power consumption. What you might notice over there is, as the ideally the system sort of idles the different CPUs, right. So if I, let's say, have 8 CPU cores, it might put them into lower performance mode, where basically what it does is saying that rather than working at 2 gigahertz or 2.4 gigahertz, it's going to bring them down and maybe run them at 400 megahertz, right, and that's sort of the idling speed. 400 megahertz is still a fairly fast speed, but it's considered, but in terms of the power being drawn by the system, as you can see, it can easily be 1/10 of the peak power that would otherwise be drawn if it was operating at full speed, right. So voltage and frequency scaling is a very powerful tool and pretty much required in order to get good performance out of modern systems. Now, power aside, the next sort of big challenge as far as SoCs is concerned is verification and debug, and it's sort of useful to think in terms of a pyramid, right. And what I mean by the pyramid, and of course this applies not just to SoCs but any kind of large system design, where basically what we have is, we start off with the so-called unit tests, which are individual IP blocks being designed at the individual block level. But once we have sort of verified that our individual blocks, let's say adders, multipliers and so on, have been verified and tested properly, we can start to integrate them maybe into ALUs or maybe into some subcomponents, right, and start to do basic integration and some level of interface verification. Once we have done that, we might go further and start, or at this point we will be basically talking about things like bus interfaces and whether the bus protocol is actually being satisfied properly. We then need to go and do verification at a chip level, right, where we essentially have a complete SoC. You need to also start looking at the software and how it integrates. But then finally you also need to go into the complete system level, because even though the idea is that a SoC contains almost all your required components, it is still having to deal with the outside world, which would be things like the actual network interfaces, the antennas, the flash drives and various other kinds of things, right. Now the reason why we sort of call this as a pyramid over here is because the maximum number of tests would be done here. It would presumably take a large amount of time, but this, although it would have a fewer number of tests, also has the potential of sort of, if you can sort of and the impact of a problem found over here would be much larger than individual problems found at this level, right. So it's not as though things get easier as you go up the pyramid, it's just that the kind of impact that it would have on the behavior of the system would change significantly. Now there are a number of different verification methodologies that are used in practice. Things like UVM are more in terms of standards of how tools like System Verilog can be used in order to build up a systematic set of test protocols or test benches, right. But by following these kind of standardized techniques, it becomes easier to sort of communicate between different kinds of IPs that are being designed and to ensure that the testing process itself is standardized. Formal verification is a very important part of the design process. It actually allows you to say that a specification and a design are in fact exactly going to behave the same way. The simulation based approaches that we have used so far, right, always have the problem that maybe I missed out on a test case, or maybe I did not try out all possible test scenarios, right, whereas formal verification tries to sort of ensure that such a problem cannot arise by formally trying to specify what the requirements are and then saying that all of them are satisfied in practice. There are other things such as emulation, which is especially used for large digital systems where you do FPGA prototyping. You use FPGAs to run a version of the hardware that can be tested and debugged at close to operational speed, and then finally you go for a real full-blown ASIC tape out. Now the verification is more at the design level, but after implementation you still have the requirement for debug, right? You need some kind of visibility into the system operation as well as control over execution, right? And some of the most common debug features are what's called the JTAG or Joint Test Action Group taps or test access ports, right? So a JTAG tap is something means by which we can get sort of access to the internals of the FPGA, or not just in general, not the FPGA, but any kind of design, any digital design can have a JTAG tap associated with it. Of course, it has to be designed this way, right? So while you are designing it, you need to make sure that the JTAG chain has also been integrated into the design. But once it has, it actually allows you to go for really in-depth capture of individual different registers that are present inside the system. You can set those registers to known values, trigger the evaluation of the entire system, calculate what the outputs, or rather read out what the outputs of each of the combinational blocks came out to be, because they get stored into the registers, and compare it against known or expected values. So it gives you a very fine grained level of control, and of course it is also time consuming, so ideally you should not need to rely on it, but it is a very powerful means of debugging. In the context of FPGAs, and as we will be seeing in the lab assignments as well, you can use what are called on-chip logic analyzers, which actually allow you to dynamically sort of measure the or observe the different signals that are present inside the logic of the design. Now, apart from power and verification and so on, there are also a number of actual security related challenges that come up in SoCs. Now, why is this an issue in the first place? It's because modern SoCs have a lot of functionality and are used for a lot of very important purposes, including things that involve actual financial as well as personally identifiable information security, right? Now, there's a reason why we use encryption, especially during financial transactions and so on, because otherwise somebody could sort of get hold of that information and then misuse it in order to interact with our bank or bank accounts. So if you want to prevent things of that sort, you want to ensure that the infrastructure built around your SoC is secure and it's not possible for someone else to tap into it and extract information from it. However, this is also a very difficult task in general, because there are numerous different kinds of attacks that can be executed against hardware or software, right, which includes things like physical attacks, where literally somebody gets hold of a phone, let's say, and ultimately by opening it up, you can almost go down to the point where you solder wires onto the JTAG access ports and directly get access to the internals of the chip. At that point, it is extremely hard to prevent the leakage of information. But there are ways even around that, right, to ensure that even if somebody has that kind of physical access, they still cannot extract information from your system. On the other hand, that's of course an extreme scenario, but there are a number of other things that could happen, including what are called side channel attacks, right, where without any specific sort of ability to break into the system that you have, it is still possible to extract information from your system. There are software attacks which are the most common probably, right, and of course from the designers or manufacturers point of view, there is this notion of IP theft, where the IP that has been used and designed and used in a proprietary manner in your system might be reused by someone without permission, provided that they can sort of reverse engineer how your system was implemented in the first place. A number of different things have been brought into SoC design to try and get around this, including what's called the secure boot process and something called the root of trust, right, which basically involves what are called either trusted platform modules or some kind of individual blocks present inside chips, right, which make it essentially very hard, if not impossible, to break into the system and reverse engineer what is the data being stored or communicated inside the system, right. Now again, this is mostly out of scope of what we are looking at in this course, but these are things to be aware of in terms of the challenges as far as SoC design is concerned. So obviously the security considerations are very likely to affect performance, because the moment you want to encrypt all data, let's say, it's adding extra computation. It's most likely going to have an impact on the power consumption and also almost certainly on the speed or the throughput of your computations. Verification of security properties is by itself a very difficult task, right? Encryption and cryptography in general are not easy to get right. So it's always in general better to sort of look for tried and tested means of encryption and security rather than trying to roll your own techniques and saying that, okay, this must be good because it looks good to me, right? Very often that turns out not to be the case in practice. So to sort of summarize this entire discussion that we have been talking about, right, there are a number of challenges as far as SoC design and implementation are concerned. There are also some interesting trends that appear as we sort of look forward to the future. One of them is what's called the heterogeneous computing, right, and this is already a very important aspect of how computing happens today, because as you saw in the structure of a typical SoC, we have a CPU, we have a GPU, we have a neural processing unit, we have custom built image signal processors, digital signal processors and so on. But there will also be more specialized accelerators, perhaps for AI ML applications, perhaps for something else, right. The integration, Moore's law, although it lasted for a very long time, in its original sense in terms of the number of transistors increasing, has sort of more or less not been going at the same rate that we would like it to, right. It's sort of arguable about whether or not it's still valid, but what is clear is that you need other kinds of techniques in order to sort of expand the capabilities of what can be put on a chip, which means that even from the point of view of the manageability of large complex designs or for putting more transistors into a single design, we need to start having more success with techniques perhaps like 3D integration or chiplet based designs, which are currently doing well but are also still components of research. There are a number of different AI assisted design and verification techniques that are on the horizon and are basically parts of research projects going on right now, that are very likely to only increase in future, because this is something, the sheer complexity of the designs that we are dealing with is so large that some kind of AI assistance looks like the right way to go in terms of how we can handle this level of complexity. And of course, just like I said, the specialized accelerators, we also have the domain specific optimizations. We already have things like cryptographic specialized hardware, but we could also have things that are domain specific, in the sense that maybe things that are only for signal processing, maybe things that are only for neural networks or AI ML kind of applications, or other kinds of things where again we see the specialization into things like low power IoT devices and so on. So the whole area of SoC design is still something that offers a lot of possibilities in terms of the kind of developments that we have, right? But the complexity is so large that you need to understand things at a very broad or a very large number of different scales of complexity or design in order to really be able to get the best out of the design that you are building.